like whatever you add or subtract to the inside, you do the opposite to the base, right? Like if you take one
Yes.
and you just
Yeah, so if you're going to say, hey, I need to replace it with, if I need to subtract 1, then I'm going to need to add 1 here. If I need to add 1, I'm going to subtract 1 here. Yes?
Can you take the derivative, the next automatically increases?
To 1. Uh-huh.
Without anything changing on the right side of the
That's right. Mm-hmm. As long as you run that power rule. Your question is, if you start with this series, n equals 0 to infinity, that power series, and you differentiate it, you're going to go to 1 here. The n comes out, and then the power comes down by 1 there. Yes, that is correct. Okay. I still need to put these two together, but one of them starts at 2 and the other one starts at 1. I said don't have any fear. We're gonna be able to do it, all right? All right, so let's actually leave the first one alone and let's start writing out this one. Like let's plug in 1, then plug in 2, and then 3, and then 4. Okay, so what would happen if we plug in 1 right now? And I'm going to write this in blue. What would happen if we plug in 1? Get 1/2, right, times 1, which is just 1/2. 1 plus 1, which is 2. So we have half of 2, which is just 1. And then x to the 1. So we just get x for that first term, right? Plus, now I would do 2, yes? And then I'd plug in 3, and then 4, and then 5, forever, right? But where am I going to start my n right now? At 2. So instead of actually plugging in 2, and then 3, and then 4, I'm just going to start my sum now at 2. See, that's called being clever. I've peeled off that first piece, right? And now these two sums start at the same place, so I can put them together.
That's kind of like how you did it with the factorial.
Exactly. It's kind of like that. I had a student in my other class say the same exact thing. Yes, it's not exactly, but it's very much the same. You're peeling off what you need so that the two things kind of match. All right, good. So let's stick this x out here in the front because it doesn't matter. Plus, now I'm going to combine both these sums into one sum. They're still going to start at 2 to infinity. And then it's going to be everything in this one, right? Plus, because it's a plus here, everything in this one. So let's put those all together into a single sum. So I'll put a big old parenthesis here. 1/2 n minus 1 times n times x to the n plus this one, n plus 1, x to the n. Y'all understand that? Oh, forgot the 1/2. Thank you, thank you. That would have been a problem. Now, let's pull out any common factors we have out of this one. So what do they have in common in there in that parenthesis? I have a 1/2, I have an n, and an x to the n, right? Okay. So equals x plus summation n equals 2 to infinity. I'm pulling out a 1/2. I'm pulling out an n, right? And an x to the n. But I'm going to choose to put that x to the n on the back side. Now what would still be in here if I pull a 1/2 n x to the n out of this first term? And minus 1 is still there. And then what would happen if I pull a 1/2 n x to the n out of this one? And plus n plus 1. And the 1's cancel. And you just get 2n in there, right? So now we have this. X plus sum n equals 2 to infinity of 1/2 n times 2n times x to the n. The 2 and the halves cancel. N times n is n squared. And you get x plus sum n equals 2 to infinity, and then n squared x to the n. Now that's your power series. But you might be asking, well, what about this x out here? It just seems weird that we have an x kind of floating out here, right? Think about what this is. Isn't this just a bunch of powers of x out here, right? Isn't it? And then we just have an additional one in the beginning, right? So this is okay to have an x plus this. What you don't want to have is like x times this. You need to push that x back through. But something happens in this problem that's kind of nice. It won't always happen this way, but it happens in this problem. What does my index start at here? 2, right? It's 2. Okay. Yeah, change it, but what do you mean change it?
To account for the first term?
Yeah, remarkably, if we actually change that index, just not change it, we're not changing anything, we're not letting n be anything. But if I just take this formula right here, forget all this, okay? Forget all this. If I give you this formula right here, right? What would it create? Well, you plug n in first, or n equals 1 in first, and what would happen? 1 squared, 1 x to the 1, which would just be x, right? Then you could say, plug in 2, then 3, then 4. Isn't that exactly the same as this? It just absorbed the x in here because the formula was perfect. Doesn't always happen that way, but it does here. That's your power series. This is your c sub n. This is your x minus a to the n. All right, what's the interval of convergence here? For this to work, you have to go back and look at when we did, like, weren't we working with this thing? You have to go back in the notes when we were in this. Like, what was the interval of convergence for this thing? Absolute value of x less than 1, because x is the piece that we were plugging in for the geometric series. So as long as you give me an x there, that power series is the same thing as the original function. Okay, so lots of things in there, right? Changing your index. All right, we're ready to move on. Eight, 7. Oh, homework. Sorry. Homework for that section. Page. This is 8.6. It's page 474, 3 through 20. Okay. All right, 8.7. I'm going to give you a little bit of like a carrot to run after here. How many of you have ever seen this before? Anybody ever seen that before? Yes? Anyone else? Yes? This is argued to be the most beautiful equation in mathematics. I'm not saying it is, because beauty is subjective, right? But a lot of people say that's the most beautiful equation there is. And the reason they say that is because, well, first of all, it's true, okay? E raised to the imaginary number I times pi plus 1 is 0. And so the reason it's so awesome, I guess, is that it has all these really cool numbers in it. E is that natural base. It's about 2.718. It's the base of the exponential function. That is that function that is its only derivative. It has all these special properties. Of course, pi, pi is awesome, right? Everyone knows that if you take a circle and you divide it by its diameter, you get the ratio that is always pi, right? It just always is that way. I is this imaginary unit that you were told about in college algebra that you were told is like kind of a bunch of BS because it's like imaginary, but it's a good number, okay? We use it a lot. Square root of -1 is I. And then you have Well, 1 and 0 don't seem that important, but they are very important. 1 is what we call the multiplicative identity. Our number system creates what's called a field. And any of you that are math majors, you'll understand what I mean later, that our number systems have to have structure. And every field has to have what we call a multiplicative identity. And 1 is the multiplicative identity. 1 times anything is itself, right? Not every set of numbers has a multiplicative identity. So, and also, how many times have we used hidden ones? How many times have we multiplied the top and bottom by the same thing? Right? A lot. Okay. Hidden zeros, right? We've used zeros before. Done it several times with geometric series. 0 is what we call the additive identity. Every field must have an additive identity. Anything plus 0 is itself. Right? So a multiplicative identity, additive identity, imaginary number, pi, e, all these great things, boom. I'm going to prove that equation is true at the end of class. Okay. Taylor series. Taylor and Maclaurin series. These are two different things. They're very much connected to each other, but they're not the same, all right? So when you talk about Taylor and Maclaurin series, it's two separate concepts connected to the same idea, all right? So we'll start with Taylor series. Okay. These are named after the mathematicians that helped generate these ideas and formulas. What's that?
The other guy.
Maclaurin?
Yeah.
I actually don't know the exact history of it. I think the book has a little thing in the margin that talks about who did what when. I don't recall it. Yeah. Okay, so in the previous section, our focus was to take a function and convert it to its power series. We relied we were dependent upon this, right? If we couldn't get it to look like that, then we couldn't do anything, right? So this section says, well, wait a minute. What if you just have a function and you can't get it to look like that? Can you still generate the power series? And the Taylor series is a formula that we are going to use that will do the same thing. It will generate a power series just like this was without us having to turn into this. So your natural response to that might be, well, why did we do all that if Taylor series is going to do it for us? And the answer is because if you can use this is faster and cleaner in general. The Taylor series is a little more involved. Today, the examples I do will be very much basic level, nothing difficult. Next class, we'll get into heavier Taylor series problems. All right. So here's the concept. You start off, suppose, that's the abbreviation for suppose. Suppose you have a function that can be written in its power series. So we are assuming that it makes sense for us to define a function as its power series, meaning it has some interval of convergence. There are values of x you can plug in for which this function makes sense. If we have a power series representation, then we're allowed to take derivatives or integrate, right? We can do that? So the natural question is, I think this is natural, you can tell me whether or not you agree or disagree, that if we write this out, it's going to look like this. C sub 0 plus C sub 1 x minus a plus C sub 2. I'm going to be writing extremely fast today, so if you can't keep up, hey, there's a video that's going to be online later today. Okay? If we write this out, all functions that can be represented with their power series should look like this. So the only real distinguishing factor between power series, different power series, is what? What's what differentiates them from one another? They'll all have x minus a to various powers, right? Right? They'll all have that part to them. If a is 0, then there will be like x squared, x cubed, right? But what's different between them? the constant. That's the part that's different, right? This is going to be something, 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 right? These numbers are the things that actually govern what, like you give me a function, each function is going to have a certain set of constants. Everything else in the power series should look the same. It should be x, minus something to the fifth, x minus something to the fourth. Does this make sense or not? You sure? So the big question is this. Can we find a formula, a general formula? Sorry, I had a little brain fart there. Can we find a general formula for C sub n? Maybe. Maybe there's a way to determine what those constants are. Understand what we're trying to do? All right, so here's how we're going to do it. Let's start out with this very clever kind of idea. What is f of a? Tell me what f of a is. So remember this line right here that I have written? This is f of x, right? That's our power series written out, expanded. What's f of a? So plug in a for x and tell me what happens. 0, 0, 0, 0, 0, c sub 0. Right? That's what c, well, I should say it this way. C sub 0 is the function evaluated at a. Right? Okay. How can I figure out what c sub 1 is? Well, you sit there and you look at it for a while, and then you realize someone already did this for you, so now I can show you what they did. They just took the derivative. Take the derivative of that function. So what happens if I take the derivative? Derivative of a constant? 0. Constant attached to a function of x. Constant comes for the ride. What is the derivative of x minus a with respect to x? Just 1. Right? Okay, so c is 1. Plus, now, what's the derivative of this thing? C sub 2 is a constant. It comes for the ride. What's the derivative of that? 2 drops out. This to the first power times derivative inside. 1. So shouldn't you just get 2 c sub 2 x minus a to the first power? What's the derivative of the next one? 3 c sub 3 x minus a squared this time. Derivative of this one. 4 c sub 4 x minus a cubed. You seeing the pattern here? 5 c sub 5 x minus a to the fourth plus dot, 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 dot. Anybody know what I'm going to do now? How did I find c sub 0? I plugged in a into the function, right? So if I'm going to find c sub 1, I should plug a into the derivative. So here's what I know. The derivative at a is just c sub 1. Let's continue it. Because right now the pattern looks like, you might think the pattern looks like this. But that's not it. Okay, let's see why.